Well, good afternoon, good morning, or good evening, depending upon where you are in the world, and welcome to today's DevOps.com webinar. I'm Charlene O'Hanlon, moderator for today's event, and I welcome you. We have a great event on tap, as always, but before we get started, we do have a few housekeeping items we need to go over. First of all, today's event is being recorded, so if you miss any or all of it, you will be able to access it later on. Following today's webinar, we will be sending out an email that contains a link to access the webinar on demand. And we are taking questions from the audience. So if at any time during today's presentation you have a question for our speaker, please don't wait, don't hesitate, just use your GoToWebinar control panel and submit your questions, and we'll try to get to as many as we can near the end of today's webinar. And also at the end of today's webinar, we are doing a drawing for 6 $25 Amazon gift cards. So please stick around. Hopefully you'll be one of our 6 lucky winners. All right, with that, we will go ahead and kick off today's webinar, which is why securing server-side JavaScript source code is so hard and how to fix it. Our speaker today is Chetan Kaneki, who is the co-founder and CTO at Shift Left. Hi, Chetan, how are you? Thanks for joining me today.
Thank you very much, appreciate it, and good afternoon, good morning, good night to all the attendees. Thank you for attending and listening. My name is Chetan Kaneki, and the interesting topic of today is securing JavaScript. So before kicking off, let's go ahead and examine the agenda, because we have a broad swath of topics that we're going to be speaking about today. Firstly, we'll speak about the characteristics of JavaScript as a programming language, because that gives us basis to understand where weaknesses lie, which are potentially exploited from the perspective of security vulnerabilities. Also, we will speak to understand the transition from client-side JavaScript, which is very ubiquitous compared to server-side. And server-side is becoming very, very prevalent with frameworks like NodeJs that has been there for quite some time, and newer frameworks like Deno, which is essentially authored by the author of Node.js. So JavaScript server-side is as critical as client-side or browser-side at this point. Now, as we understand these security vulnerabilities, examine the landscape, we will also look at the proposals to measure security effectively, given the weaknesses that we speak of. And finally, we'll close with a demo where we'll conduct a series of threat modeling exercises, and thereafter examine if these exercises can be taken and automated into your CI/CD pipeline so that all your projects, albeit JavaScript or written in any programming language, can be measured for security efficacy. So to kick off, let's double click into the characteristics of JavaScript. As we know, JavaScript is hugely popular. I presume that all the audience attending today are authors writing programs in JavaScript, either full-time or context switching between backend and frontend, which is part-time. So majority of the web applications or thick clients written today are 100% JavaScript from a front-end perspective. And JavaScript is also becoming very, very popular, like we touched on the server side. And also full-fledged operating systems are being written in JavaScript. And, variety of machine learning frameworks, like TensorJS or TensorFlow.js also is being accommodated for JavaScript as well, given its popularity. So to understand the characteristics, let's go ahead and start double clicking into what it means and what does JavaScript encompass. Like I mentioned, JavaScript is a object-oriented language to start with. And some of us are potentially coming from Java and C++ background. And by that, I mean object-oriented means there's a rigid idea of objects and classes. It also happens that JavaScript is a dynamic, weakly typed language with first-class citizens. I will draw emphasis in detail of what I mean when I use terms like dynamic and weakly typed. But by weakly typed, I mean that there is no strong type system in JavaScript. There is, in essence, that we are not measuring for strictness of types. Of course, you have TypeScript, which was invented with that very cause in order to improve the efficacy of the language. But yet, when it's transpiled, all that type information is lost. Now, there's another aspect to JavaScript, which is they often say it is a prototypical language. We will double click into what that means shortly. But just to give you a gist of what it means, it relies mostly on prototyping instead of inheritance to share and extend functionality. I'll again double click into that in the successive slides so that you understand what I meant by the statement. So we spoke of weakly typing. Let's examine what we mean by weakly typing. On this slide, there is a set of functions or snippets that demonstrate what I actually meant by weakly typing. So let us start with an object. Person is an object. The person object is initialized with properties and behavior. Properties is a name, and age, address, etc. Behavior is essentially, some characteristic associated with that particular object. You could say, move money, is address valid, etc. So what you see out here is we define a property, person, and then we add person.wife dynamically to that existing property, person. And then we define behavior on the wife property that we add, which is set wife. And by virtue of accessors and mutators, we are looking up these properties associated with the object. But in comparison to a very strongly typed object-oriented language, you would have otherwise said class person, name string, address string, wife name string. But here what you see is the ability to dynamically add properties and behavior in the code as you progressively write code. So that in itself can become an issue, which we'll touch on later, which could lead to exploits. Now let's double click into the second aspect that we touched on, which is functions do not require type annotations for input parameters and return type. Now we have a very simple function out here, which is function add. It takes two properties, A and B. It adds the values and then returns the value. But what you examine here is there is no type information. It doesn't actually say A number, B number, return number. So by virtue of this, you can effectively do an addition by passing two numbers, 1 and 0. Of course, you get 1 as a result. Or you can pass hello and world, which are strings, and you get a concatenated representation, which is hello world. Due to the lacking of strong type annotations to the parameters and the return type, any type can be substituted, which again in itself could lead to issues. Now let's double click into the third aspect of it, which is JavaScript allows a variable to modify its type based on the context of its usage. If you notice here, the variable x is initially defined as a number, and then we apply a not operator twice, which converts the variable to Boolean type. Next, the variable is cast to a string and concatenated with another string. And applying the not operator twice casts the string to a Boolean type. And finally, two strings are concatenated, which converts the integer to perform subtraction. So notice that there is so much of variability in the type based on the context and the usage through the control flow of your program, which in itself can serve to be an issue that we'll touch upon later. As we spoke of in the prior slides, we touched on a critical aspect of object-oriented programming languages, right? So some of us are coming from the world of Java and very strongly typed languages like Rust and C and C++. So we either use definitions or abstract definitions like class or struct where we effectively are saying this is an entity, and the entity has properties: first name, last name, address, identity number. And then within the confines of the entity, you provide a constructor, and then you provide behavior, where you're providing accesses and mutators like get first name, last name, etc. So here, if you notice that we are defining an abstract type, we are almost creating a template to say, if you create an object of this type, you have to adhere to this specification. And if you pay attention to the lower right-hand side, you create an instance of the class, which essentially is an object, where you say string person is equal to new person, and you give it a definition, where if it effectively comes to life in your program. And everything else thereon is measured to this template and specification. Now, this is how a strongly typed language looks like. And it's relatively easy to measure for efficacy from a security perspective, for bugs perspective, when you have this something like a template out here. Now let's switch gears and look at JavaScript. We touched on this point that it is a prototype-based language. So with the prototype, it supports dynamic addition of members to objects. But let's kind of double click into what this prototype means. A prototype-based language has a notion of a prototypical object, which is the object used as a template from which the initial properties are derived into the new object, right? So we earlier spoke of class person, that's your template, and then you create instances of it. Likewise, in the world of Java, you have this prototype object, and then as you create new objects, it derives its specification from the prototype object, which allows the, almost like sharing of properties, meaning you can map or create properties into the prototype object, and then every object, by virtue of its lineage, inherits from the prototype object. Now, this in itself is a great feature because it provides extensibility. But where issues come on forth is there are a broad swath of exploits that happened not too long ago called as prototype pollution, which led for attackers to inject or extend the prototype object, polluting the very essence of objects that you've defined within the scope of your application. And that in turn led to data exfiltration, command injection, and so on and so forth, leading for the attacker to take control of the application or pull data out of your application. So now we spoke of the features of JavaScript, and then we also touched on the fact that JavaScript is not just prevalent on the browser on client side. It has also bled due to its efficiencies into the server side as well. And because it has become such a popular language, the skills that engineers have developed on the client side can be brought on forth to implement programs on the server side as well. But where the fundamental shift happened is that now attackers can attack your server-side applications, which has a higher risk as compared to client-side, because now they can effectively touch the storage units of your virtual machines, your physical hosts that are hosting your applications, and which further leads to taking control of your virtual machine, your host, or laterally move into your infrastructure and exfiltrate data. In terms of research, there's not much of research that has been done so far, which means that it's progressively done to identify and understand how we can protect server-side applications written in Node.js, which is a JavaScript variant, more effectively. Now let us examine the landscape of vulnerabilities and the expansive scope of open source packages that exist in the Node.js community. Chetan Karande wrote an excellent book on O'Reilly, where he speaks of patterns in node package vulnerabilities. I would encourage my listeners to subscribe to O'Reilly and definitely read this. To get a sense of the spread, we effectively have almost 500 plus packages created per day on the NPM repository, and an average of 603 vulnerabilities that have been accepted and have active CVEs associated to them in this landscape. And over 700,000 packages exist in the NPM repository as well. And as of today, we have about over 1,000 unique advisories, meaning that you have somewhere between accepted CVEs and those that are registered and confirmed. And if I draw your attention to the right-hand side of the screen, you almost have a percentage spread of the type of vulnerabilities that have been confirmed in these advisories and these 603 unique vulnerabilities that exist as well. And if you notice, about 28% with the lion's share is insecure access to the file system, which is someone having the ability to evaluate a command through an API route that your functions are exhibiting, and effectively take control of your application or exfiltrate data from your application. So the plethora of vulnerabilities that are existing and actively being introduced into this realm of NodeJs packages that exist in your repositories. Now, like we spoke of, broadly, most of the OWASP related categories are applicable into the JavaScript world as well, because OWASP is doing a fantastic job of creating higher level representations of categories of vulnerabilities, so that albeit which programming language you use, eventually all these categories very well fit into that specific programming language and has a broader scope. So if you look at the advanced type of attacks that are being introduced, because Node.js in itself provides packages, and these packages have characteristics like providing database access or database drivers to MongoDB or NoSQL or PostgreSQL, etc. There are newer vulnerabilities like NoSQL injection that are being introduced. And all of us, as good citizens, try to conduct validation on any input that we receive. So sometimes most of these validation routines are based on regular expressions where we are measuring for something. And in such cases, we have regular expressions used, which could potentially lead to what they call as RDoS, or regular expression denial of service. And we also spoke of prototype pollution. This is becoming very prevalent in the attack landscape. And the last one, which is the most popular, is what they call as using components with known vulnerabilities, which is if you happen to be using an open source package, and that open source package has a certain characteristic, if used in a certain way, can lead for a vulnerability to happen in your application. Now, let us look at how security tooling is advancing to ensure that you have an instrument to measure for these vulnerabilities. Because firstly, we spoke of JavaScript. We spoke of the challenges, because JavaScript is weakly typed. It is a prototype language. It doesn't have effective type checks. And then properties or abstract types or templates can be adjusted and changed anytime in your program. So these qualities in JavaScript pose a high degree of difficulty for security instruments to measure for vulnerabilities in JavaScript. So for that, let's sort of step back and look at how interpreters and compilers reason about your code. The first step that any compiler interpreter does is it analyzes your source code and builds an inverted tree, which effectively is called as the abstract syntax tree. And the syntax tree is almost synonymous to looking at, suppose you have a statement, var a is equal to b plus c. You have operators and operands. The operators are equals to sign and plus sign. The operands are c, a, and b. So think of it a way where it literally takes the operators and operands and builds an syntax tree out of that. And once the syntax tree is built, it is effectively evaluating to check whether it adheres to the programming language grammar. Because every programming language has a specific grammar. And as good citizens of using the programming language, we have to ensure that we adhere to that grammar specification. So that's what the job of the syntax tree is. Now, the second aspect of it is control flow. Now, as we write code, we are writing various statements like if check for logical validation or truthiness, where if you're saying if A is equal to B, or if condition is equal to true, then execute a particular command, or else do something else. So control flow is all about this, where the language provides you constructs and you utilize these constructs to measure for how control should flow in your code. And finally, there is this the compiler construct called as call graphs, right? Where every programming language provides a high-level abstraction of functions. So we write a block of code, we fit it into that function, and then we begin to optimize our code by breaking it down to several functions, further down to microservices. So there's a concept called as intra-procedure and inter-procedure flow, which means that if I have various statements, they're either all fitting within a particular function, or there's a call sequence of these flows across various functions. So as the interpreter and compiler reasons about your code, they're effectively examining the call graph, meaning how function A calls function B, how does your router, which is, if you have an API endpoint, calls a specific function, which in turn calls a handler, which in turn connects to your database. So all of these three constructs are critical for a compiler and interpreter to reason about your code. Now, as the state of art with JavaScript from a security evaluation perspective, unfortunately, is somewhat restricted to the abstract syntax tree alone. Because JavaScript in itself is fairly complex, because it has no types, it's prototypical in nature. You can fundamentally define the quality of the prototype or the object anytime in your code. Majority of the security tools today restrict themselves to measure for code conditions that are bad in your code. Meaning, suppose you use an eval statement, suppose you use a certain construct in MongoDB, like find one. What state-of-the-art security tools today do is they create a series of regular expressions, like what you see on the screen. Particularly if I draw your attention to that JSON blob in the center, you have a method signature, eval, which is nothing but a regular expression. And the parameter section says, this eval statement is accepting a request or a request.query, a request.body, request.param. In this case, which almost is indicating that it's accepting the request directly, because in the world of JavaScript, it's convention over configuration, where you tend to use REQ as a request that is accepted from the outbound into inbound. So if you notice, method signature and parameter are regular expressions, and the state-of-art security tools are almost doing semantic grepping, where they combine both of these, they look for patterns in your code, and eventually tell you that user control data or attacker control data from the outside is being directly piped to this sensitive function called as eval. And that would potentially lead to remote code injection. And the reason that the state of art is only restricted to grepping using the syntax tree is that you cannot fundamentally do very strict data flow in your code, which is the second two parts, which is control flow and call graphs, simply because there's lack of type information. And the research community is still coming to terms with how to effectively build a system that would enable to precisely say that you have something coming from the outside through the control flow and your call graph that would lead for this vulnerability to exist. But let's look at the issues that lie with semantic grepping. Plenty of false positives, because you might have an eval statement lurking in your code that is not controlled by an attacker from the outside. So although the security tool might cry out loud saying this is a vulnerability, it might not necessarily be a one, right? Because it's not controlled. The other is, an issue called as catastrophic backtracking of regular expressions. It's something that we call as regular expression DDoS. When you heavily depend on regular expressions, the issue is at some point when the evaluation engine runs, if the expression is not well formed, all of us have dealt with regular expressions. At some point, you would have realized that, some expression of yours is taking an inordinate long time to execute or analyze, and it's consuming 100% of your CPU. That happens because of this issue called as backtracking. And if you Google that, you'll get enough information. And the proof of this that happened not too long ago is the Cloudflare CDN was down for over about 5 to 6 hours because they suffered from the same issue of catastrophic backtracking. And lastly, no semantic context. If you just merely grep for a statement in your code, you're not looking at what leads to this statement from the outside. Is there a control? Is there data flow, et cetera, right? So all in all, false positive, which means more work for the engineers to navigate this and solve this problem. Now, again, we spoke of the state of art now. So let's gleam at a code snippet and see what this means from that context. Now, as good citizens, what we do is procure various tools to ensure that the security efficacy of our system is measured for continuously. So if you look at this code snippet, it typically represents a Node.js module, where the first line, which is boxed in red, is you requiring a set of system libraries or open source libraries that you have incorporated in your application. Of course, you want to always stay on top of ensuring that you use libraries that are not vulnerable. So the best bet is you go out and use an Node.js scan, which is an open source representation, or you go ahead and subscribe to a vendor. And the best that this vendor or this open source tool can do is it looks at your package.json or your required statements, picks up the versions, and looks up a CVDB database and tells you straight up that you're using a vulnerable version. But it does not understand whether you're actually using it in a certain context that lends for it to be vulnerable. Now, the second aspect, the second red box, is this eval statement, right? If you're using a security tool, the best that it can do is regular expression pattern evaluation, like we spoke of. And note that both of these are sort of independently done because you're using tool one for a software composition analysis and the second for pattern analysis of security sensitive functions. And what you have to do also is engage and procure a third tool to correlate both of these and see if it makes sense, so that you send signal to your engineers rather than noise for them to address these issues. Now, we at Shift Left have been examining how we can solve this problem better. And the genesis of Shift Left as a company came about based on a fundamental technology that was invented in the academic realm called as code property graph. Our chief scientist, Dr. Fabian Yamaguchi, challenged himself that grep cannot fundamentally be the tool of choice because there are all these issues that it's plagued with. The compiler has these three interesting constructs called as the syntax tree, the control flow, and the call graph, which is used by interpreters and compilers. So why not actually combine all of these into a unified representation? Because you need the context of the syntax, meaning how things are defined. You need to understand control flow so that you see whether you're conducting validation or not for anything coming from the outside. And finally, you need to look at call graph, meaning how function A is calling function B is calling function C, and what is the context of the attack from that perspective. So on that basis, he essentially authored his PhD thesis to invent code property graph, where he combined these three techniques together, and he placed on it what they call as semantic data overlay, which is how an attacker can move from the outside, meaning how can he touch an API endpoint, take control of a parameter you have on that API, move inwards, and touch a security sensitive function to exploit your application. So this complex graph that you see at the bottom is nothing but the ability to query your code to identify how the attacker is actually exploiting your application. More so, we also spoke of the fact that there are various types of programming languages, which is strictly typed like Java and Rust. And then you have weakly interpreted inference types like Python, and then weakly typed like JavaScript. So upon this graph, he also provided the ability to provide type hints. Type hints for weakly typed languages is cues to tell you that we don't really know it's that type, but we are inferring that it could be this type by examining what is happening from a data flow perspective. Meaning if you perform a math operation, it's most likely a number or a string, because if you do a string A plus B, it's a concatenation operation as well. So with these type hints, what we can do is somewhat begin to precisely tell you that these are the type of vulnerabilities that can be applied on your application to exploit. So fundamentally, with the invention of this, we recently onboarded JavaScript. We put a lot of effort on this because it was the hardest endeavor to take on compared to a typed language. So we are very excited to release support of code property graph for JavaScript, which means that you can evaluate your Node.js applications go forwards to identify for vulnerabilities very precisely compared to the other vendors who are doing state of art with semantic prep. Now, let's look at it from a code perspective. You have, Taint flow that we spoke of, where if you combine all of these three structures together, suddenly the insights become very interesting, very pointed, that can enable your engineers to do better analysis. So I want to draw your attention to, I'll walk you through each aspect of this visual, the same code snippet. But if you look above, using the graph, we understand your SCA context by virtue of looking at your package.json, all of the libraries required, which is imported, which actually means you're using the library. And then in the line 5, which is the second section where I'm moving my mouse, there is a create server, an HTTP server is being created through a framework where you have an endpoint listening on a socket, which accepts a request and creates a response. And upon this, there is a series of web routes that are being mapped so that your users can interact with these routes. So by looking at the syntax tree, the control flow, and data flow all together, we can almost create an attack surface of your application, saying almost like if you're using Swagger to create your API spec, we auto create this API spec where we tell you that here is your read function, it accepts a request, it uses a response, and by the way, request, you have certain elements of your request, extracted or in your source code, where data elements are, if you're dealing with streaming data or a certain other element of that request is taken out, like requested URL, etc. So with this, we can start creating very interesting insights. First of all, we tell you this is an entry point for an attacker. We also can tell you that, by the way, the entire request is being logged to the console, which in this case is violation of compliance. Because assume your request contains sensitive information about your user, correlating the user to the session, PII data of your user like address, etc. Because as good engineers, often we like to log as much so that our logging aggregators can provide us insights so that we can search for it, triage, and debug and trace. But where we falter is we log too much. And when that happens, we are in violation of compliance. So this, by data flow, we can tell you straight up that there's a request being received, it goes to console.log, and by virtue of this, you're in violation of PII and compliance like SOC 1 and SOC 2. Thereon, we identify that you have a route that has a function like move money, which is a route controller function that accepts this request. And inside the move money, you have a streaming loop where you're gathering that data through a listener by virtue of assembling the chunk, and on that basis, you're conducting some function like move, essentially auth or capture on that transaction. And somewhere in the middle, you have an eval, which is after you assemble the chunk, you're passing it to an eval function, which is dangerous. So now, rather than just doing regular expression on eval and just saying this is a bad function, we are telling you precisely that you have an exposed API endpoint, and you are not doing any validation. You're just doing chunk assembly and directly passing it to the eval function. So with this, we can very straight up tell you that there's a sensitive sync of eval directly connecting to a source function, which is your entry point, which is read. And by the way, this is susceptible to SSJI, which is server-side JavaScript injection and command injection because of the sensitive function, which is eval. And just to summarize what I described, looking at the request parameter passed through the move money, we understand that some attacker can effectively pass a require file system function, which is a system library available in Node.js, look up your etc password, and exfiltrate that data in your response. And likewise, they can spawn a child process and induce command injection on your application. So this is the amount of detail that we can get at to tell you whether you are susceptible to a vulnerability or not, by virtue of not just having regular expressions, but actually combining the three structures, which is the syntax tree, the control flow, the data flow all together, and then creating these interesting flows and then examining it further to let you know whether you are actually really susceptible to an attack or not. With this, I'm going to switch into demo mode, but you're welcome to explore this by yourself after this presentation. We've created a exploitable Node.js application called as EXPL NODE, which is hosted on GitHub on this link, github.com, Kaneki C, which is my handle, and EXPL NODE. I will walk you through the code shortly, so we'll quickly switch into presentation mode at this point. So EXPL NODE is an application that is intentionally seeded with various types of vulnerabilities. But just to make it a very interactive exercise, these vulnerabilities have been slotted into different files. Each one of them is a controller in itself that is holding symptoms that exhibit the existence of this vulnerability. So if you just click one of them, if you notice that there is a controller called as ping, and there is an exec function, which effectively is directly piping the request body URL and then conducting a response send. So symptomatically, each of these files are exhibiting these conditions that would lead for a vulnerability to be triggered. And in this case, you have a run me function, which effectively spawning a child process. So there are a plethora of representations of typical vulnerabilities in this file called, in this particular folder called as vulnerabilities. And likewise, pairing with it is a folder called as Ocular Notebook. And I will shortly walk you through what Ocular is and how we conduct threat modeling with Ocular, which is a tool that we provide for advanced security companies so that you can create your own signatures. You can use our signatures to extend your existing signatures for advanced threat detection. So what Ocular is almost like a query language. If you're familiar with MongoDB, PL SQL, Shift Left provides an underlying platform where we first of all analyze your code, we create a graph and place it in a database. And then Ocular is a query language over this database where you can begin to ask interesting questions of, am I susceptible to an SQL injection, a command injection? And then you can begin to write your own queries, just like you would for PL SQL, where you write your select statements, your insert statements, and then you export that and conduct continuous checks in your CI/CD pipeline. So what Ocular is, very quickly, if I shift, if you head to our website and you navigate to products and Ocular, it somewhat describes what Ocular is. And if you wish to get hold of a trial license and use this project to navigate your findings, feel free to do that anytime, please, after the presentation. So what we'll do right now is fire up Ocular. Like I mentioned to you, Ocular is a distribution that we provide, just like a PL SQL or Node.js or MongoDB. All you have to do is install Ocular and type this command SL Ocular. And once you do that, it will go ahead and fire up a command line prompt, which would let you interact with your application. Your application could be a JavaScript Node.js application where you first load the application and begin to ask interesting questions on the application. So once we have the the command prompt ready, what we'll do is conduct a series of threat modeling exercises so that we get a sense of what are these vulnerabilities, what do they actually mean from a perspective. So the first thing that I'm going to do is execute these three commands. I'm just going to cut and paste them. The first command is codepath. I just cloned this project in local space, and I'm going to execute a command called as import code, where I'm going to pass this path. The first thing it will do is pull this project into my session, create the graph, and make it ready for me to conduct investigation upon it. The second command I'll execute is just, we provide you a set of batteries included policies. So this command says run.security profile, where the graph is created, is going to quickly analyze the graph and understand all potential vulnerabilities that exist in your code. And this is a default function that we provide you as baseline, so you don't have to do any work. It automatically does it for you. Now, as soon as I run this command, what you get as a context is when I execute cpg.finding. CPG stands for code property graph. .finding, essentially saying, have you found anything that is vulnerable or exploitable in this code? To JSON pretty. And voila, you got a series of findings. And I'll speak to at length about what all of these mean. But effectively, you have OWASP categorized set of findings, which are automatically deduced without doing anything, just executing two commands. And the richness of these findings is where it goes beyond grep, is it tells you that we found something of type SQL injection. And by the way, it maps to a CV MITRE number 89. And then we provide details of the flow associated with it, meaning we give you information of what an attacker can do from the outside by taking control of a parameter, and then how it flows through your code, which is the data flow, to eventually reach a security sensitive function that can be abused to trigger an exploit. But before that, let's just run a few examples so that we get a sense of what all of this, how does this cook out? How this command has a lot of intelligence, but let's look at what is happening behind it. The first is I'm creating a simple function, get dependencies. What your SCA vendor would charge you a few $1,000 to do, which is look up your dependencies, map up against SCA. That can be done in two commands. In this command, we give you all your dependencies. We have, with our licenses, provide you a aggregated database across multiple sources where we can actually tell you whether you're using a vulnerable function or not. What it was trying to say is you get that for no cost with the entire secured broad swath of security tools with shift left. Now I'm going to execute a series of signatures, just as examples, so that you get a sense of, how your application looks like, what is the shape of your application, and where these potential vulnerabilities lie. So I created a very simple function, get attack surface. It's almost like what your Swagger API would do. I'm going to call this function and say, get attack surface for this graph, the CPG for this application that I've created. Now note, what you get here is an entire breakdown of your method controller and the route that your application is exposing to your customers and attackers. So this is typically a first step to understand your exploitable attack surface in your application. Of course, this doesn't imply that everything can be attacked, but you almost want to start somewhere to first identify, okay, I have a list of functions that are, a list of routes that are exposed. Now let's deep dive and look at each parameter in this route that an attacker can take control of to touch security sensitive functions in your code. So for that, we're going to do a series of very quick exercises. Firstly, given that we have the attack surface, I'm going to just type in a very simple command saying, on the CPG, give me every exposed route and map it to a local variable called a source. Now, once I have this, it means that we make an assumption that every exposed route is exploitable. Now we want to see whether your code contains any patterns that would lead to command injection. So here we have remote code injection based checks. So here it is trying to identify if you have any method of type exec, spawn process, because these are commands that someone can take control of, especially when you have it exposed without doing any validation of the input that would lead for this command to execute. So I'm marking any method of type command injection because we have a plethora of signatures that are sensitive commands in your application that we check for. We are marking all such commands to this variable called a sync. And the last thing that we do is sync reachable by source dot flows. It's a very simple check where we are saying, we took all your sources, we have a sensitive sync. Now let us know whether any source function can touch the sensitive sync without validation. And lo and behold, we do have a condition. And if you notice, you get a very neatly pre-printed representation of it with the file, the line numbers associated with it, the function, and the attacker controlled parameter that is exposed on the route, which is tracked. Now, with this, you're almost getting validation with certainty that you, first of all, have an exposed route, you have a sensitive function, and there is a flow from the exposed route to the sensitive function without validation, which actually implies that most certainly someone can induce a server-side command injection. And this becomes now proof for your engineers to triage, debug, and resolve very effectively. Let's execute one more command so that we understand, what are the other types, very complex types of conditions that we can find. Now, we spoke of denial of service attack. We have, if I navigate to the code and pick one of these files, which is loop.js. In loop.js, we have list users, and we have the body.users, which is fetched and assigned to an local variable object. And then we initialize an array and then iterate the object and push values into this array. Now you could imagine someone can create a very extensively large object, users list. And this in turn can cause this array to exceed the memory threshold, which in turn, if continuously executed, would lead to a denial of service on your application. So this is a fairly complex check because we're going to look for several things here. We are looking for here's an exposed route. You have a request passed to a variable, and inside the confines of this code block is there a for statement, which is a control statement. The control statement could be for, while, loop, etc. It could be anything, right? Now, is any of the attacker control variables passed to this control within the control statement? And if so, all of these conditions together potentially could lead to a denial of service. So let's execute this and see, because we're looking at various checks here. And most certainly the first thing we're going to check is a very simple call. And what I'm showing you here is a lot of internal threat modeling, which means that if you have advanced security teams, you can do a lot of this of what you see. But when you use our inspect product or a shift left scan product, all of this is automatically done for you. So without lifting a finger, all of this is done for you. I'm just showing it so that you understand the complexity of what we can do with JavaScript. Now with this very simple command, we are saying cpg.call.code memory op, which means in your code, are you conducting any memory-centric operation, like either a list operation, an array operation, or a caching operation, either be cache validation, cache invalidation, etc. And then in your syntax tree, is there any control structure that exists? So when we execute this single statement, you get proof that within this code block, we do have a control statement that exists. And of course, what we want to do is go one step further to ask whether this control statement, can it be influenced by an attacker? So by executing and assigning this to a sink, the next question that we ask is, can any of those exposed sources touch a function within this looping construct? And lo and behold, of course, yes, you get a flow. And note that the critical difference between us and any other vendor or an open source tool is regular expressions can tell you that you are using a sensitive function. But where we can go one step ahead is tell you that there is a data flow from the outside that can influence that sensitive function in a way that would lead for a particular type of exploit. And that type of exploit is denial of service in this case. So I'd encourage you to go through this project step by step, because there are a variety of use cases. All of them have been documented succinctly out here so that you understand the different types of attack vectors that we can identify, the sensitive data leaks that we can identify. And if you go through this exercise, you get a sense of the efficacy at which we can discover vulnerabilities in your system, and also provide you the ability to go one step further and configure your own set of findings. And lastly, I'd like to close with, all of this complexity exists if you're using threat modeling and you have advanced red teams and blue teams in your organization. But if you have an organization that is fairly small, but you want to stay on top of your vulnerabilities, then we provide a shift-left SaaS foundational platform where you very quickly hook up this analysis in your CI/CD pipeline like Jenkins, Travis, Circle. Automatically with a single command, we can identify any vulnerabilities. We provide you build rules so that it can automatically fail your build. And then beyond vulnerabilities, what we can also do is provide you secrets detection, which you otherwise have to go procure another tool. And again, secrets we can detect at a higher efficacy compared to majority of the open source tools that exist like Trufflehog and few others, because we have a very broad dictionary that we have configured by learning from various compliance and regulatory institutions and a broad swath of customers where we've really seen issues. With this, you get a broader scope of findings and a very comprehensive Swiss Army knife-like tool, which provides you a single glass pane to identify critical ones, secrets, insights, all in a single glass pane. And you can take all of these insights, plug it to your Jira and other ticketing systems, or directly hook it into your GitHub issues so that it becomes a very dev-centric tool and provides you enough information with high precision so that you're not wasting time sifting through false positives. So with that, in closing, we have demonstrated advanced threat modeling, a tool with high degree of efficacy to identify security vulnerabilities through data flows, and then automatic evaluation through your CI/CD pipelines using our shift-left SaaS tool. So I'd like to close and then open the forum to questions. And thank you.
All right, great. Thanks so much, Chetan. We have about 6 minutes to the top of the hour, so I think we have time for one, maybe two questions. Let's see what we got here. Okay, here's one. Is Ocular only for JS, or does it support other frameworks like Java, Python, etc.?
It supports a broad spectrum of languages. At the moment, we support JavaScript, Java, C#, which is the .NET family, Golang. Shortly, we're going to support Python and Rust as well.
All right, great. Let's see. Next question here. Let's see. These scripts of checks, would it work on any Node.js repos, or is it specific to this vulnerable repo?
The scripts are tuned. It's mostly an interactive tutorial, but it has a broad applicability. When I executed this one API called cpg.findings, that works across any project because the signatures that we have created are common across any project. Because our goal is not to make you do work, but if you'd like to create your own scripts, then you could leverage and understand how these APIs work and go about creating your own. And that's the purpose of this tutorial.
Okay, great. I think we have time for one more here. Let's see. Oh, here's one. I am impressed. Are you planning to use this technology for other platforms such as C#?
Absolutely. We already support C#. And we have a broad variety of customers using C# in production.
Excellent. Okay. All right, let's do one more, and then we'll be done. Which IDE are you using?
If I grokked your question correctly, if you're asking about which IDE I was using in my presentation, it was Visual Studio Code. But if you're asking which IDE do we support, given that we have plugins for IDEs as well, we do support plugins for Visual Studio Code in the marketplace.
Excellent, excellent. Okay, well, we're about 4 minutes to the top of the hour. Unfortunately, that's all the time that we have for the question and answer period. If we didn't get to your question, I apologize, but please note that the folks at Shift Left are getting a copy of all of the questions, and so they will be more than happy to follow up offline with you to get your question answered. Let's see, I did say at the top of the hour that we would be doing a drawing for 6 $25 Amazon gift cards. So let me go ahead and do that real quick. Let's see, our winners today are Claude N. Congratulations, Claude. Jamie S. Congratulations, Jamie. J.T. Congratulations, Jay. Myron L. Congratulations, Myron. Let's see. Pat B. Congratulations, Pat. And our last winner today is Juan A. Congratulations, Juan. We'll be following up with all 6 of you offline to get your Amazon gift card over to you. So please check your inbox. Also want to remind the audience that today's event has been recorded, so if you missed any or all of the event, or if you just want to watch it again, you'll have the opportunity to do so. Following today's webinar, we will be sending out an email that contains a link to access the webinar on demand. And the webinar is also going to be living on the devops.com website, so you can always go look for it there. Just go to devops.com/webinars, look in the on-demand section, and it should be right there waiting for you. Chetan, thank you so much for such a great presentation today. Lots of really great information and lots of really great questions that came in from the audience. So judging from those, I know they got a lot out of it. So thanks again, appreciate it.
Thank you very much. Stay safe, stay healthy.
Yes, thank you. Also want to thank the audience for joining me today. This is Charlene O'Hanlon, and I'm signing off. Have a great day, everybody. And as Chetan said, please stay safe,